All right, guys. Good afternoon. So it's about 3:30 on Wednesday, September 3rd, and super happy to have all you guys with me for this virtual MIS 373 class. I'm currently sitting in the Nashville airport. Had to go out for a business trip overnight, so apologize I couldn't make it in class, but we'll try to get through this as efficiently as we can. And for your benefit, those of you who couldn't make the class, this session will also be recorded into YouTube so that you can view it in at a later time if needed. I've also posted, if you have any questions, you can post into the Google Plus event page, and post your questions. Also, feel free to ping me if you'd like to be invited to the Hangout on Air to speak live on on the Hangout. All right. So I think so. My normal pace of classes, I kind of explained last time. I like to start off with some interesting news or happenings in the tech world, and of course, I think what's captivated the tech world as well as larger society over the past few days is this whole celebrity photo hack that was well covered by the general mainstream press. What's been interesting is if you look at the tech community's response, particularly Apple, who normally does not respond to press inquiries on investigations or upcoming products, they actually responded this time, and they used the word outraged, which indicates that they felt very strongly about this event, this hack, if you will. And what's been interesting, as I've been reading through some of the backstory, it almost seems like the folks who hang out on hacker forums like 4chan have found a couple of exploits that they've chained together to make this thing happen. And what's interesting is, one, it was a vulnerability in Apple iCloud, the fact that it did not reject multiple attempts to log in with different passwords. And they exposed the ability to log into the Find My iPhone service via API, the application programming interface, kind of the way that you would address a service, just like you would address the Java virtual machine through a Java API. And so some folks were able to write a script that you could test 500,000 or 1 million commonly used passwords if you knew the intended victim's email address. And so I suppose they were able to get into some of these accounts successfully that way. Now, what's interesting, especially those of you who use iPhones and iCloud, you'll know that generally speaking, the photo stream feature only stores the last 1,000 photos or so. But in this case, what's happened is it's been speculated that through a piece of software written by a Russian company called Elkomsoft, that's used by law enforcement agencies to be able to actually pull down an entire copy of a user's iOS device backup and restore it onto like a virtual device, if you will. And so once you've got a backup of someone's device, you could just go through it at will. And so this is kind of a scary security problem, and I don't think anyone's had enough time to digest and figure out what do we do about this in the future. And so kind of moral of the story is that, as with so many things in the tech industry, it's a security versus convenience debate. So yes, it's more convenient to use a simple, easy to remember password, but it makes it less secure. Correspondingly, it's more secure to use two-factor authentication, but then it's less convenient because that means you always have to have that second factor token, like your smartphone or an RSA token or some other code generator, always nearby you when you want to log into a given service that's got two-factor turned on. So, public service announcement of the day: if you use Google services or iCloud, turn on two-factor authentication, and the likelihood of an event like this happening to your account goes down to a very infinitesimally small percentage probability. So that said, let me jump into a screen share right now, and I'll go over the content that we had covered from last time. All right. So as I was explaining about towards the end of class last time, the Java programming language is built, you can think of it in a layer model. There's a multiple layer model. So at the very bottom, you've got your host platform, which would be your underlying operating system, whether it's Windows, Mac, Linux, Android, could be one of the IBM mainframes, Solaris, any number of platforms that have had Java ported to it. Above that runs the Java virtual machine. And this is what actually turns any Java application and allows it to run on any given host system. And so if you think about the way traditional applications, or apps as we now call them in the mobile world, are written, you have Windows applications, you have iOS apps, you have Android apps. None of these applications are interchangeable between different platforms. And the reason for that is because the app or application has been written specifically for the host platform's API. And so your Candy Crush Saga on iOS was written to be an iOS app, and therefore it cannot run on Mac or Windows. This is in contrast to a Java application which is written for the Java API, which runs on top of this Java virtual machine. And so you have this intermediary layer that allows any arbitrary Java application to run on any host platform that supports the Java virtual machine, in principle. The running joke, of course, is that Java was intended to be a write once, run anywhere has become write once, debug everywhere. All right. So let's go on to the next slide here. So here we see the sort of a diagram of how the Java virtual machine works. And on the left, you have your Java source code. This is the Java source code files all have a .java extension to them. And this is where you would write your code, define your functions and methods. If you want to write hello world, it would go inside a .java file, hello world.java. To actually turn human written code into code that a machine can recognize and run, we have to run it through a compiler. And so you may be familiar with having written Visual Basic code in the past. You have to compile the VB code in Visual Studio, which then gives you an exe file that you can run on a Windows system. Similar concept here, except the Java compiler, which is typically javac.exe on Windows or just javac on Mac and Linux. What it does is it takes in as an input the Java source code and produces as an output something called bytecode. So Java bytecode is platform neutral, and it's stored in a file that has the .class extension. And so you take your hello world.java, run it through the compiler, and then as an output you get hello world.class. And you need a compiler that's capable of running on the specific platform that you're using at the moment, because it has to be able to run locally, doesn't have the benefit of being able to run on top of the Java virtual machine, and it takes the Java source code and turns it into bytecode that can run on the JVM. And so then you get a Java virtual machine, typically a Java interpreter, which is java.exe on Windows. And again, each of these JVMs has to be platform specific. So one for Windows on x86, one for Mac x86, one for Solaris on Spark, one for Linux on ARM or what have you. And then it's this JVM that takes the Java bytecode from the .class file and then is able to actually execute it and take in user input or produce output and run as you, the programmer, expected it to. All right. So, all right, next I want to talk a little bit about three different types of Java applications. So the first type of Java program that you can write is an applet. We don't see these too often anymore, but they're still hanging around on the web. So what an applet is a Java application that runs inside a web browser. And so if you've ever wanted to play like some game, or I think the old Blackboard editor actually wanted to use, was a Java-based Java applet. So it would require your PC or Mac to have a JVM installed and a plugin for your web browser. And then the Java application would run wholly inside of the web browser, inside of what's called a sandbox for security purposes. Applets have kind of fallen out of favor because turns out they're not as secure as we thought they were. It's also fallen out of favor because newer web technologies like Adobe Flash or HTML5 have made it possible to have very good levels of interactivity, really cool features, logic, all sorts of stuff that wasn't possible in the early days of the web unless you had a Java applet. The next kind of Java program we see are just standalone Java applications. And these are programs that will run directly on the platform through the JVM, and they are distinguished by the presence of a method called main inside the .java file. And the main method is the entry point for the application. That's where your code is going to start executing from. And so if you've got a file, like a program like Hello World, you may only have one statement in the main method. That's where the JVM is going to start execution. It's going to look inside of main, see that you've only got one statement, like system.out.print hello world, execute it, and then terminate. In a more complex application, this is where you would have all of your other function calls to start executing on the desired logic or functionality that you've intended. The third kind of Java program are servlets. And so these are Java programs that run on servers as opposed to running on a client. And so the server would be something likely stored in a data center, and it responds to typically an HTTP or HTTPS request. And that's the input for the servlet, and then the servlet's output is some formatted HTML that gets displayed on the client as a web page. And so this allows the website to have more interactive, dynamic content that's processed on the server side instead of on the client side. So notable examples of this are many banks. If you've ever done online banking, a lot of their code is written in Java as a servlet running on the server side, but all you see on the client side is just a bunch of HTML. And so if we look at the evolution of Java, how did we get here? It's been in the mainstream since about the mid-90s, so it's almost 20 years old at this point, which is relatively young as far as languages go. I mean, we've seen a number of popular languages come up in the last several years, but compared to things like C, C++, BASIC, Assembly, Fortran, the list goes on, Java, in the grand scheme of things, is one of the newer languages. It's got a huge developer base. It's still the #1 programming language out there. And maybe I can take a look here. And so if we see, we've got an index of the top programming languages. Oh, and it looks like Java has finally fallen from its place as #1, and I'm surprised that C has overtaken it. Yeah, for the longest time, Java was the #1 language, in large part because it's taught in schools, such as here. Yeah, and we see #3 is Objective-C, and that's how applications for Mac OS X and iOS are written. And so that is kind of a testament to the popularity of the iOS and Mac platforms. And then you see sort of the list as you get down there. You've got your C# and Python and Perl going on down, and Pascal's still hanging out down there. So yeah, just if you're ever interested, the TIOBE has a list of top programming languages. So Java's out there just all over the place, and it's got just the install base is in the probably hundreds of millions of PCs. But if you include non-traditional platforms like mobile devices, almost every feature phone out there. I mean, if you think back to like the dumb phone, that old Samsung phone that you had like in the early 2000s that could only make and receive calls and maybe text messages. Some of those run Java. Many of those run Java, in fact. Some of these smart cards that you may see where it's got the little chip built into the card, that may run a variant of Java. Probably the most prevalent install base of Java-enabled devices are Android devices. So Android applications are written in Java, and so every Android phone or tablet or non-conventional Android devices like refrigerators all carry a JVM on board to execute that Java bytecode and actually communicate to the host platform and do something useful. So I'll talk about Eclipse next time in class. I'm going to skip that for now just because I'm not on a Mac at this time, and so I don't have Eclipse on my Chromebook. So I'm going to pause here and see if there are any questions. It doesn't look like there are any questions quite yet in the G+ event. Okay. So with that, I'm going to start off on sort of some basics about the Java programming language. So we've got our requisite Dilbert slide, Dilbert comic here. So I'm going to try really hard in this class not to have super dense slides because it just means that it's harder to retain information that way. One aside, someone once told me, especially if you guys are going out on office visits to prospective employers, if you're going on an office visit and you look around the cubicles and around the hallways, take a look at how many Dilbert comics and nowadays XKCD comics are posted on cubicle walls. And there's an inverse relationship to the number of comics and the level of employee happiness or morale at a place. So if you see lots of Dilbert comics, run. All right, so we're going to talk about the basic building blocks of Java and about some variables and what we call primitive data types. So first thing to talk about are identifiers. So identifiers, that is how you name anything in a language. So it could be a variable, it could be a function, it could be a class, could be a package. Anything with a name is going to have an identifier. So in Java, we are case sensitive. This is probably the biggest point I need to make to new Java programmers, is that it is case sensitive. Uppercase A is different than lowercase a. The other thing is that you cannot begin with you can't have a digit as the first character, and you can't have a reserved word. So you can't have a variable called null or false. And so we see on the left examples of some legitimate identifiers, and over on the right you see examples of identifiers that are going to fail. And so the first example, we can't allow a hyphen. The second example, you've got a numeric digit in the first place. You can't have that. Third example, goto. Goto is actually a reserved keyword, even though no one uses goto in Java, but it's still out there as a reserved keyword. And then finally, the fourth example that's bad there is because it starts with a digit. So case sensitivity, so you see 4 variations on the identifier, your name. And each one has different capitalization, and each one is going to be unique. And there's actually a naming or capitalization convention. And so if we see the first example where it's all lowercase, that's for a package. And we'll cover packages in greater detail later in the semester, but packages are groupings of classes. The second example is for initial caps, and that's for a class. And so any class which is used to create objects, so sort of a class is sort of the most basic building block of Java, you're going to use initial caps. In the third example, methods and fields, so variable names, are typically the first letter of the first word is lowercase, and then subsequent words are capitalized. And then finally, constants are all caps, and a constant is any kind of variable that's going to be immutable or permanent. And so examples of this would be pi, or speed of gravity, or distance of the Earth to the Sun. Things that in your code are going to remain constant. So on this slide, we see a list of reserved keywords. And you're not going to have to memorize these, but over time, as you start working in Java, you're going to see these keywords come up over and over again. And just be sensible and don't try to name your variable integer or float or something like that. And there's a couple more reserved keywords that aren't actually implemented, but they are still reserved, and so you cannot name your variables after these. All right. So comments. Hang on. Let me just see if any questions. If anyone's got questions, again, please do post to the Google Plus event page. So comments. So really, so great programmers like to say that their code is self-commenting, but that's almost never the case, and it almost always falls to the junior programmer or the new guy or new girl on the team to have to do maintenance work on someone else's code. And so that's where, if you want to be kind and pay it forward, you'll put comments in there also to help yourself remind yourself of, hey, what the heck am I trying to do here? And so 12 months later or 24 months later, you can come back, look at this thing, and say, oh, okay, this is what this piece of code was trying to do. So a couple of different kinds of comments. The first one is just a single line comment, so //. The second kind of comment is more typically seen, and that's going to be a multi-line comment where everything in between the slash asterisk and asterisk slash is a comment. And so this is where you can write, if you want to, you could write a long form paragraph about what is the purpose of this program. You typically find lengthy comments like this in the first dozen or so rows, first dozen or so lines of a particular application. It just gives an idea about who's the author, when they wrote it, any copyrights that may be applicable to this code. And then the third kind of comment is specific, and that begins with /*, and that's for a system called JavaDoc, which is used to generate documentation for Java programs and functions. And so a great example of this is if we actually go out and look at the code, or excuse me, the documentation for the Java programming language itself. So actually, let's look up system.out. And yeah, the documentation from Oracle, this is all written in JavaDoc. And so the reference material for the Java programming language itself is produced using JavaDoc, and you can also document your own code, produce a documentation guide for your own code using JavaDoc. And so it just gives a nice breakdown between what are the variables and what are the various methods that apply, how to use those methods. And this is all stuff that's written via comments. And it's important to note that comments do not affect the output of the program. So one error I have seen folks make is if they forget to close off their comment, then and they start writing a whole bunch of statements, then all the statements after the initial comment, the start of the comment, all of those statements will be considered comments by the Java compiler, and they will not compile into code. All right, next, statements. So a statement is any single line that you want to tell the computer to do, right? And in Java, every statement is terminated by a semicolon. This means that just because you press enter to create a new line doesn't mean that's the end of the statement. So in Java, statements can actually wrap across multiple lines, and so you need to be very explicit with your semicolons. So if we see the example here, a system.out.println, my actual string that I'm going to print out is on the second line, but it's all considered one statement by the Java compiler because there's only a single semicolon. Now, you don't have to put the example in the green box, you don't have to put multiple statements across multiple lines. They can all be globbed together onto a single line. So here we're just assigning some numbers into variables. The only caveat here is that for readability, it makes it more difficult because your eyes, as you're scanning through code, tend to look at things all in a single line as a single statement. And I think that's just from habit of having written code and read code that was written across multiple lines like that, like usual. So yeah, do yourself a favor and put each statement on its own line to make things easier. All right, so we're going to talk about primitive data types. And so when I refer to primitives, I'm talking about data types in Java that don't need to be declared as objects. They just kind of exist natively as a basic building block, almost like the atoms and electrons of the world. You don't need to really define them because they They just are that way. And so if we think about integers, which are whole numbers with a sign, positive or negative, there are different types of integers available, and they vary by how much memory space they're going to take up. And so a byte in this case is literally just 1 byte, 8 bits, that's used to represent a particular integer. And so if you look at the byte data type, the byte data type goes from -2 to the 7th to +2 to the 7th minus 1. So that's 255, right? And so the, oh, excuse me, it's 127. And so we've got, if you look at a byte which is 2 to the 8th, because you're going across positive and negative, you're limited to only 127 in either direction, really. And then we move on to a data type called short, which is 2 bytes. And so if we think about what are the range of numbers that we can represent with 2 bytes, you would think it's 2 to the 16th, but it's actually 2 to the 15th, because again, we have to go across both positive and negative, and so this gives you a range of roughly minus 32,768 to positive 32,767. And it's always -1 because you've got to include 0 in there. Then int is going to be the most common type of integer, and an int is represented as 4 bytes. So again, quite a big range at this point when you're getting up into the 2 to 31st power. That's a pretty decent chunk, right? So just yeah, it's what, roughly about 2 billion in either direction. And then finally, long is 8 bytes, and then this is for really big numbers. And so we're offered several different primitive integer data types because, especially if you're working in a memory-constrained environment, think back to like 1995. How much memory did PCs have back then? It was measured in megabytes, right? And then in today's world, your smartphone may have a gig or 2 of RAM, but it wasn't always that way. And there are embedded systems that remain today that power things like cars or smart cards, or maybe an ATM machine or something that has not a gig of RAM, but may only have like megabytes of RAM. And so you want to be able to optimize for the data type that you're going to be using. And so if you're measuring temperature on Earth, you could probably, or temperature in Texas at least, you could get away with using a byte. It wouldn't make sense necessarily to use an int and chew up 4 bytes of memory if you're going to be measuring a temperature swing in Austin from maybe -5 at the coldest to like 115 at the hottest. All right, let's check for questions. Any questions so far? Okay. All right, not seeing any questions quite yet, so we'll keep going. So, floating points. So, floating point numbers are called this because they've got a decimal point in them, and so this is your general number. So, pi would be an example of a floating point number, as opposed to an integer that would was only whole numbers, right? And the floating point numbers are limited to two data types. So you've got your float, and then you've got double. Float being 4 bytes, and double being 8 bytes. And you see here it's represented in scientific notation, and it can go out for quite a bit. And so you've got some, and the difference between these two really comes down to precision. And so I'll tell a story about where this matters. So a long time ago I worked on the microprocessor for the Sony PlayStation 3, which was made by IBM. And the decision was made to, and if you guys have played PS3 or Xbox 360, and then certainly the new generation Xbox One and PS4, its signature hallmark in these gaming consoles is the excellent graphics. And it takes quite a bit of math to drive the polygons and shadows and reflections and all that stuff that you see that make the images look so lifelike. And it takes quite a bit of math to drive that. However, the processor for PlayStation 3 was optimized around what's called single precision floating point. So it would be roughly analogous to your float data type. And the reason for that is because when you're thinking about graphics, things, if you're playing a first-person shooter, things are happening really fast, and so you need really high frame rates, but you don't necessarily need to see excruciatingly high detail if things are flying across the screen at 60 frames per second, right? However, we got a request from the U.S. government, from Los Alamos National Labs, to take a derivative of that same chip that was used in the Sony PS3 and optimize it for supercomputing. So supercomputing refers to, in this use case, the Los Alamos National Lab needed a fantastically fast machine that could handle highly precise math in order to simulate the degradation in age of nuclear weapons. And so rather than blowing up a bomb in the desert that is 50 years old to see what happens, they could model what the aging and decay effects are by just using a supercomputer simulation. And in that case, being almost good enough is not really an option. You need to be exceedingly precise. And so we had to take the original Sony PS3 chip that was optimized for single precision floating point, and then optimize it, tune it for double precision floating point. And so that means that every time you did like a multiplication, it would take up, really like 4x the amount of memory, because you've now got, two really huge sets of numbers, that potentially huge in the sense that, after the decimal point it could go on and on and on, and then multiply those together without losing precision. So it was a pretty exciting project, and really drove home the point about what's the difference between single precision and double precision floating point numbers. All right, a character. So a single character is considered a primitive, and it's a unsigned, what's called Unicode character. And so Unicode is the character system that all modern computers use to represent letters, numbers, and symbols across all the myriad of different languages that we have, single byte languages that we have. So, so languages like Cyrillic and Greek, and certainly all the Roman-based languages, all of their characters fall into the Unicode character set. This is where you also get the some of the funky symbols like heart and arrows and If you want to, I mean, some of you guys probably have seen folks write in emoji. It would kind of be like this, and those are all part of the Unicode character set. And then next primitive type, we have our Booleans. So Boolean is a true-false value, and it's initialized to false. And kind of a key thing I should mention here is that an int cannot be used in place of a Boolean. This is as opposed to if you've ever done C or C++. Folks have actually, I mean, I used to when I was doing C++, you could get away with, representing a Boolean as like a 0 or a 1. But in Java, just being a little pickier wants everything as true or false, not 0 or 1. So we see here that we've got an example, several examples of literals. So a literal is just any primitive value. And so you've got the 5 kinds of literals that map to the primitives that we just talked about, your integer, float, Boolean, character, and then another special kind of literal called string. And a string is denoted by double quotes to enclose it, and a string is just a sequence of characters all together. And so the phrase "hello world," if it's encased in double quotes, would be considered a string literal. So, talking a little bit about primitive literals for integers, you can use different bases. So, obviously, we normally count in base 10, but if you want to work in octals or hexadecimal, base 8 or base 16, you can represent it as a literal. And so, like a hexadecimal is represented by 0x followed by, from 0 through F. And you will see, if you've ever seen like a blue screen of death in Windows, you'll often see lots of hexadecimal numbers. And these refer to memory addresses. So in your computer, every computer out there, memory space is written in terms of hexadecimal numbers. And so if you want to address like a particular piece of memory, you could do so by referring to its hexadecimal address. And for a long, if you want to refer to a number as a long data type in the literal format, then you would append a capital L to the end of it. All right. So float. So floating point data types. If you've got the short float, which is the 4-byte float, then you would append a uppercase or lowercase f to it. Otherwise, the default is to look at something to take a decimal point number and refer to it as a double. So if you want to be explicit about a number being a double, you could append a D to it, or if you see the 4th bullet down here, a floating point number with no final letter is considered a double. So 3.14 is automatically considered a double unless you appended an F to it to indicate 3.14F as a float data type. And the 3rd bullet here, you can see E is used for scientific notation. All right, I think I'm going to stop here, and let's see if there are any questions. And we don't have any questions here, so you guys are being a quiet bunch today. So, all right, that's all we're going to cover, and so we'll pick up next time in class on Monday. And otherwise, I will. I'll go ahead and I might send out some instructions on getting Eclipse up and running on your computers, and then we'll try to nail down a due date for that first assignment. So if you guys have any questions in the meantime, please feel free to shoot me an email, Edward D, as in David, at utexas.edu. All right, y'all have a great rest of your day. Take care. Bye-bye.